Recording is rolling. It is Friday, May 9th. You guys have your quantum journals out, ready to go. And we're going to do number 13 through 16 today. Got 13 through 16 queued up. All right. So, we're closing down the year, starting to clean out my room. You guys remember all those top scientist lists? All right, so, been saving them since August. They're all over there on that lab table because they're over there on my lab table. So, hey, since it's Mother's Day weekend, if you want to grab one of those that has your name on it, take that home, then, well, those are free. So, those are for you guys if you want them. And so, first one today, number 13, got quantum tunneling. Quantum tunneling.
Suppose you drop a ball down the side of a valley. Classical wisdom tells us that when the ball rolls up the hill on the other side, it can't go any higher than the height from which you dropped it. That's conservation of energy. Even if there's a nice big long slope to roll down on the far side of the mountain, the ball just can't get there, unless you give it enough energy to get over the barrier. But in quantum mechanics, things work a little differently. You see, the quantum world is probabilistic, so if you release a particle in a valley, chances are the next time you see it, it'll still be somewhere in that valley. But if there's a nice big slope to roll down on the far side of the mountain, well, that's a place the particle would really like to be. And it turns out there's also a small chance that's where you'll find it. If this isn't crazy enough, it's even possible you'll find the particle in the middle of the mountain. And in real life, this means that an electron sometimes hangs around inside the nucleus of an atom.
Some of us were taught in high school that the electron orbits around the nucleus, like a planet around the sun. However, this description has been understood as a gross misrepresentation for the better part of the last century. As it turns out, there is a characteristic uncertainty related to the very small. No one can tell exactly where something is. The best one can do is figure out where something is most likely to be. We can visualize this with something called a probability cloud. Here, we see the probability cloud of a proton at the center of a hydrogen atom. The denser regions are where the proton is more likely to be found. However, this uncertainty is not due to an inability of ours to measure the small in the exact manner. It is a fundamental aspect of the world in which we live, and its implications are extraordinary. Let us take, for example, the phenomenon of tunneling. If we can't tell exactly where something is, then it follows that we can't tell exactly where it's been or where it will be. The best we can hope for is where it most probably will be. So there's a small chance that a rocket ball thrown repeatedly at a barrier should just tunnel through the barrier, appearing almost magically on the other side. We don't see this often because a rocket ball is pretty big and its uncertainty pretty small. But if we deal with matter on the subatomic scale, it becomes much more likely. Here our projectile approaches the barrier. We see here its probability cloud. Although it's most likely near the center of the cloud, we can see that there is a small chance of it being on the other side of the barrier. And so, sometimes, it is. Tunneling isn't a mathematical trick or an assumption. It's an observable fact. It's made use of commonly in modern electronics, and in a real way, allows for life on Earth. To see why, let us trace the creation of a photon in the sun. The light from the sun that we see reflected off the moon, the light which drives the Earth's weather, that provides the energy for life, all originates from the process of nuclear fusion in the sun. Two light atomic nuclei collide, forming a new element, and in the process, light is released. But these nuclei are both positively charged and so repel each other. Only if they have enough energy can they overcome this potential barrier and fuse. But if you do the math, the nuclei in the sun don't have enough energy. The sun's just not hot enough. Nonetheless, the sun shines, and it does so because of tunneling. Just like our physical barrier, there's a chance that our particles will be on the other side, and so the sun shines.
Ooh. Okay, so you guys know that in quantum mechanics, if you're trying to find the location of, say, a particle, well, it's going to be a probabilistic answer. Say if I go back a few days ago to, you guys remember Schrodinger's equation, the wave function. Okay, so here's like a one-dimensional location axis and a certain probability where it finds something. So like if you talk about classical mechanics, you definitely have like some definitive position of something, right? Then quantum mechanics is probabilistic, right? Got Heisenberg uncertainty, you can't really even know precisely, right? So let's represent the location of a particle with a probability cloud, right? Probability cloud, right? Where it's more likely to be in the center, and maybe like there's a 90% chance it's towards the center, but maybe a 10% chance somewhere out on the periphery. Okay? And if you have some barrier here, which I'm representing with this wall, there might even be a, say, a 1% chance it could be on the other side. So if you make repeated measurements, so suppose you have like thousands of electrons, right? You make thousands of measurements, okay? Sometimes you'll find it where maybe you wouldn't expect it otherwise. Okay? So what could this help explain? So a couple I picked up from there was, he said, actually his last example was nuclear fusion in the sun. Okay? So if you say, what's the temperature and the pressure, say close to the core of the sun, and what's the amount of energy that radiates away from the sun that comes out of nuclear fusion, it doesn't exactly 100% add up unless you also consider this quantum tunneling effect. Okay. And the other example I got out of there was, you mentioned modern electronics. And for that, I have a graph for you guys. Did you guys catch up to about there? Okay. So, question: how many of you guys know what is Moore's law? Who knows? Who knows what is Moore's law? You may know that one. Ooh, right. Right. So, sometimes it's stated as some version of technology periodically doubles, or the amount, the number of transistors you can fit on a computer chip will periodically double. Okay, I have a graph version of this. Say graph version. So here, these are all commercially released chips. Right? So it's sometimes like how many transistors can you economically fit onto a computer chip? Right? And so these are all commercially released chips. Like this one here says ARM 700. Looks like it was released in 1994. Okay, so that's one of a bunch of them on here. So we got a time axis down here, horizontal. It goes from 1970 to 2016. So 1970, 72, 74, 76. All right, so it looks like the time is scaled linearly. Right? And if you stand back and look at this, hey, does this look like pretty much a straight line? Do you guys see it? If the line is best fit and zip right through there, right? Okay. Okay. Well, what is the vertical axis though? You see transistor count. How many transistors can you fit on chip? But what is this, guys? Is this scaled linearly? 1,000, 10,000, 100,000, a million? Ooh, logarithmically. Aha. So this curve right here, as a function of time, it isn't actually linear, is it? It's actually what? Starts with an E. Exponential. It's an exponential curve, isn't it? Right. And so this is just a law of nature, economics, manufacturing, right, put together. Right, so law of physics. Right. But can this go on forever? Well, probably not, because and this tunneling might be one reason why. Okay. Because at some point, if you're trying to represent bits, just zeros and ones with particles that are too small, jammed too close together, say like electrons or photons even, okay, there's only so closely you can pack them together, and then you run into this probability cloud problem. So yeah, so Moore's law is probably going to have an end at some point, but yeah, for many decades, 1970s to 2010s on this paper, that's not for a long time, but probably not forever. All right. This next one. All right, you guys ready for quantum entanglement? So a little bit of forewarning. Right, this is one of my longer videos. Got a Veritasium video for you guys. This one where I'd have to watch this one a few times to start to wrap my mind around it. I mean, I'll play it once, but if this intrigues you, you can always do more Google research yourself too. So buckle up.
In the 1930s, Albert Einstein was upset with quantum mechanics. He proposed a thought experiment where, according to the theory, an event at one point in the universe could instantaneously affect another event arbitrarily far away. He called this spooky action at a distance because he thought it was absurd. It seemed to imply faster than light communication, something his theory of relativity ruled out. But nowadays, we can do this experiment, and what we find is indeed spooky. But in order to understand it, we must first understand spin. All fundamental particles have a property called spin. No, they're not actually spinning, but the analogy is appropriate. They have angular momentum and they have an orientation in space. Now we can measure the spin of a particle, but we have to choose the direction in which to measure it. And this measurement can have only one of two outcomes. Either the particle's spin is aligned with the direction of measurement, which we'll call spin up, or it is opposite the measurement, which we'll call spin down. Now, what happens if the particle's spin is vertical, but we measure its spin horizontally? Well, then it has a 50% chance of being spin up and a 50% chance of being spin down. And after the measurement, the particle maintains this spin. So measuring its spin actually changes the spin of the particle. What if we measure spin at an angle 60 degrees from the vertical? Well, now, since the spin of the particle is more aligned to this measurement, it will be spin up 3/4 of the time and spin down 1/4 of the time. The probability depends on the square of the cosine of half the angle. Now, an experiment like the one Einstein proposed can be performed using two of these particles, but they must be prepared in a particular way. For example, formed spontaneously out of energy. Now, since the total angular momentum of the universe must stay constant, you know that if one particle is measured to have spin up, the other, measured in the same direction, must have spin down. I should point out it's only if the two particles are measured in the same direction that their spins must be opposite. Now, here's where things start to get a little weird. You might imagine that each particle is created with a definite, well-defined spin, but that won't work, and here's why. Imagine their spins were vertical and opposite. Now, if they're both measured in the horizontal direction, each one has a 50-50 chance of being spin up. So there's actually a 50% chance that both measurements will yield the same spin outcome. And this would violate the law of conservation of angular momentum. According to quantum mechanics, these particles don't have a well-defined spin at all. They are entangled, which means their spin is simply opposite that of the other particle. So when one particle is measured and its spin determined, you immediately know what the same measurement of the other particle will be. This has been rigorously and repeatedly tested experimentally. It doesn't matter at which angle the detectors are set or how far apart they always measure opposite spins. Now just stop for a minute and think about how crazy this is. Both particles have undefined spins, and then you measure one, and immediately you know the spin of the other particle, which could be light years away. It's as though the choice of the first measurement has influenced the result of the second faster than the speed of light, which is indeed how some theorists interpret the result. But not Einstein. Einstein was really bothered by this. He preferred an alternate explanation, that all along the particles contained hidden information about which spin they would have if measured in any direction. It's just that we didn't know this information until we measured them. Now, since that information was within the particles from the moment they formed at the same point in space, no signal would ever have to travel between the two particles faster than light. Now, for a time, scientists accepted this view that there were just some things about the particles we couldn't know before we measured them. But then along came John Bell with a way to test this idea. This experiment can determine whether the particles contain hidden information all along or not. And this is how it works. There are two spin detectors, each capable of measuring spin in one of three directions. These measurement directions will be selected randomly and independent of each other. Now, pairs of entangled particles will be sent to the two detectors, and we record whether the measured spins are the same, both up or both down, or different. We'll repeat this procedure over and over, randomly varying those measurement directions to find the percentage of the time the two detectors give different results. And this is the key, because that percentage depends on whether the particles contain hidden information all along or if they don't. Now, to see why this is the case, let's calculate the expected frequency of different readings if the particles do contain hidden information. Now, you can think of this hidden information like a secret plan the particles agree to, and the only criterion that plan must satisfy is that if the particles are ever measured in the same direction, they must give opposite spins. So, for example, one plan could be that one particle will give spin up for every measurement direction, and its pair would give spin down for every measurement direction. Or another plan, plan 2, could be that one particle could give spin up for the first direction, spin down for the second direction, and spin up for the third direction. Whereas its partner would give spin down for the first direction, spin up for the second direction, and spin down for the third direction. All other plans are mathematically equivalent, so we can work out the expected frequency of different results using these two plans. Here, I'm visually representing the particles by their plans, their hidden information. With plan 1, the results will obviously be different 100% of the time. It doesn't matter which measurement directions are selected. But it does for particles using the second plan. For example, if both detectors measure in the first direction, particle A gives spin up, while particle B gives spin down. The results are different. But if instead detector B measured in the second direction, the result would be spin up, so the spins are the same. We can continue doing this for all the possible measurement combinations, and what we find is the results are different 5 out of 9 times. So using the second plan, the results should be different 5/9 of the time. And using the first plan, the results should be different 100% of the time. So overall, if the particles contain hidden information, you should see different results more than 5/9 of the time. So what do we actually see in experiment? Well, the results are different only 50% of the time. It doesn't work. So the experiment rules out the idea that all along these particles contain hidden information about which spin they will give in the different directions. So how does quantum mechanics account for this result? Well, let's imagine detector A measures spin in the first direction and the result is spin up. Now, immediately you know that the other particle is spin down if measured in the first direction, which should happen randomly 1/3 of the time. However, if particle B is measured in one of the other 2 directions, it makes an angle of 60 degrees with these measurement directions. And recall from the beginning of this video, the resulting measurement should be spin up 3/4 of the time. Since these measurement directions will be randomly selected 2/3 of the time, particle B will give spin up 2/3 times 3/4 equals half of the time. So both detectors should give the same results half of the time and different results half of the time, which is exactly what we see in the experiment. So quantum mechanics works, but there is debate over how to interpret these results. Some physicists see them as evidence that there is no hidden information in quantum particles, and it only makes sense to talk about spins once they've been measured. Whereas other physicists believe that entangled particles can signal each other faster than light to update their hidden information when one is measured. So does this mean that we can use entangled particles to communicate faster than light? Well, everyone agrees that we can't. And that is because the results that you find at either detector are random. It doesn't matter which measurement direction you select or what's happening at the other detector, there's a 50-50 probability of obtaining spin up or spin down. Only if these observers later met up and compared notebooks would they realize that when they selected the same direction, they always got opposite spins. Both sets of data would be random, just the opposite random from the other observer. That is indeed spooky, but it doesn't allow for the communication, the sending of information from one point to another faster than light. So it doesn't violate the theory of relativity. And that, at the very least, would make Einstein happy.
Ooh. It's the wild ride there. So if you have these entangled particles, say you have a couple of particles that are entangled, and then you separate them, because of the law of conservation of angular momentum, they have to have exactly opposite momentum, right? But then there's this quantum aspect to this, which is that the angular momentum, the spin is not really well defined to begin with, right? It's all probabilistic, right? Just like the location of some particles is probabilistic, right? But you can measure the spin, but the act of measuring sort of affects reality too, right? But if you measure one, the spin of one particle. Now, if you measure the other particle in the same direction, it's always exactly the opposite, right? But what about at some other angle? And then that kicks back to probability, right? Now, scientists were trying to figure out how do we interpret this about 100 years ago or so, okay? And one of the possible ideas that was floating around was, well, maybe by measuring one, it's going to lock in one spin, right? Maybe the information has to immediately travel to the other one faster than light, right? That'd be one way to interpret this, right? But that would raise some problems, right? Like Einstein would say, well, that would violate my theory of relativity, that nothing can travel through space faster than light, including information, right? So right, now enter John Bell in 1964. It says, hey, actually, I can go with an experiment to test which way this actually is, right? Is it that there's hidden information all along that's just being revealed by these measurements? Or could it actually possibly still be the case that information is somehow traveling faster than light, which would be crazy, right? And that was most of the video you guys saw with these detectors at 120 degrees from each other. They got 120 degree angles, right? And we're measuring all different ones, right? And depending on exactly the proportion of results you get from those detectors, it would tell you which way it is there hidden information or not. And it looks like this experiment indicates that there is no hidden information. So it is still possible that information is traveling faster than the speed of light. Okay, but which is really crazy because that has some crazy implications. Okay, like you guys know from relativity, nothing can travel through space faster than light, including information, right? Which only travels like at the speed of light. Okay, now there's a couple of like weird sort of I don't know if I want to say like exceptions to that rule, but maybe French cases that sort of stretch that rule to its limit. Right? One is the expansion of space itself. Because of the expansion of space, if you get two galaxies that are far away enough from each other, space can expand between them so that the galaxies are traveling faster than light relative to each other, but they're not traveling through space at light speed or faster. It's just that space is expanded between them. So that's kind of okay, one of those fringe cases. And this is the other main fringe case: is what about entangled particles? Is there really information traveling faster than light? And it looks like the answer might be yes. Right? Now, there's one more addendum to this, which is, well, can you then use that to send information like useful information faster than light? Like, could you send an email to Mars in a fraction of a second? Suppose we have people on Mars by the end of the century, and we have like a Martian base, and we're trying to communicate by email. So we're sending some email across space to Mars. And I'll say just spacing the planets in some season ends up being like 10 light minutes, just to make up a number, right? So at the speed of light, it would take, say, 10 minutes for an email to reach Mars. Could you take advantage of this quantum entanglement to get that email there faster than that? Let's say instantaneously within a fraction of a second, right? And here's where everybody agrees, no, you cannot do that because an email would be useful information, whereas this quantum entanglement is always random, so random information. Okay, so really weird corner of physics right there. All right, you guys got quantum entanglement? I said, all right, so a couple down, a couple to go. Today, ooh, fate and free will.
Newtonian determinism says that the universe is a clock, a gigantic clock that's wound up at the beginning of time, and it's been ticking ever since according to Newton's laws of motion. So what you're going to eat 10 years from now on January 1st has already been fixed. It's already known using Newton's laws of motion. Einstein believed in that. Einstein was a determinist. Well, does that mean that a murderer, a horrible mass murderer, isn't really guilty of his works because it was already preordained billions of years ago? Einstein said, well, yeah, in some sense that's true. Even mass murderers were predetermined, but he said they should still be placed in jail. Heisenberg then comes along and proposes the Heisenberg uncertainty principle and says, nonsense. There's uncertainty. You don't know where the electron is. It could be here, here, or many places simultaneously. This, of course, Einstein hated because he said God doesn't play dice with the universe. Well, hey, get used to it. Einstein was wrong. God does play dice. Every time we look at an electron, it moves. There's uncertainty with regards to the position of the electron. So what does that mean for free will? It means in some sense we do have some kind of free will. No one can determine your future events given your past history. There's always the wild card. There's always the possibility of uncertainty in whatever we do. So when I look at myself in a mirror, I say to myself, what I'm looking at is not really me. It looks like me, but it's not really me at all. It's not me today, now. It's me a billionth of a second ago, because it takes a billionth of a second for light to go from me to the mirror and back.
All right, so here's a big question floating around in sciences and literature is how much free will do you have, or how much of your actions are just fated to roll out? Now, there's, again, a different perspective. So if you take a psychology class, this normally is framed as nature versus nurture, right? Like, why does anyone make any particular decision? How much of that is framed by, say, like the culture you grow up in, or like if you make a decision, how many options are you choosing from? Suppose you're choosing from 3 or 4 options, and those are framed by it's like your family environment or like the ideas that you're exposed to have to choose from to begin with anyway, right? Where do your thoughts come from? And how could those be like multiple choice options in the whatever options you choose to navigate your life? Um, is it something like 50-50, like 50% environmental and 50% is actually your free will, or is it like 80-20 one way or another? Right? Really kind of open questions, kind of hard to answer those questions in some ways, right? There's like twin studies, right? So some identical twins are separated by birth and then they find them like 30 years later and they compare their lives and they can sort of suss out some similarities and differences that way, right? So what's the physics perspective on this? The physics perspective, oh, well, I got a billiards table here for a pretty good analogy is what if you have, say, this billiards table and you strike the cue ball with the cue stick, right? Now, suppose you're filming this with the camera, so you're making a video, and right after you strike the cue ball with the cue stick, you get a few frames and then you pause the video, right? Now, right at that moment, if you know the mass and the velocity, let's say the momentum of the cue ball, right, and you know the locations of all these other balls, isn't what's about to roll out in the next few seconds exactly determinable? Right? Like if you're really good at billiards, like as soon as you strike that cue ball, you can say, oh well, once it's set in motion, it's gonna like bounce off this ball, or off this wall, and off this ball at this angle, and it's gonna send that ball into the corner pocket, right? Like that is determinable in the next few seconds, right? Well, if you take that Newtonian determinism to its logical end, you say, well, your brain is just made out of the same matter as everything else in the environment. And so here I've just got like 3 or 4 balls rolling around, but you could multiply that by a factor of like billions or trillions and say in a certain, from a certain perspective, like the decisions you made are results of chemical reactions, right, which just boils down to physics, right? Like if you try to go eat lunch. What triggered that in the first place? Well, it was maybe because you felt hungry, and maybe that's out of like some biochemical reactions that set off that chain of motion, right? That chain of events. So, oh yes, if you talk to either Isaac Newton or Albert Einstein, who also bought into this determinism, they might say, well, maybe the future is just, in effect, just going to roll out, right? Like whatever's going to happen in the year 2100 is just kind of sitting there waiting, just like the past is in your history textbooks, and that's just baked and set, right? Maybe the future is set in a similar way, and time is just playing it out, and whatever free will it feels like you have, maybe you have a lot less than that, right? Maybe zero at an extreme. Oh, now if you bring in quantum mechanics, now there's a lot more uncertainty. Right, there's this Heisenberg uncertainty. We don't know exactly where an atom is. There's the Schrodinger wave equation, which is where any particle is probabilistic. Right? So if you think about those biochemical reactions going on inside your brain, which is driving a lot of your actions, there's a lot more uncertainty associated with that. Okay? Could that possibly open more door for more free will? Maybe, right? Or maybe there's a third aspect of physics that we don't know. Because is it possible also that that consciousness itself is something that is difficult to quantify in terms of kilograms, meters, seconds, and amperes, and maybe we don't have a clear understanding of that, and that's possible too. And so a lot of open questions on that one, but there's a quantum mechanics perspective on that. Okay. All right, so we got one more today. Actually, this last one here, I'll just flash one of my posters up here. So they're considered to be 4 fundamental forces in nature. Right? Actually, this is right on this page is the answer to the first review question from yesterday. You guys remember yesterday we were finishing the study guide, and the first question was the fundamental force underlying all chemical reactions is. Okay? And the answer is right here. Right? So electromagnetism. So in this class, like in a high school physics class, the main 2 forces you care about are these top 2: gravity and electromagnetism. That covers almost everything that shows in this class. Right? So you got universal gravity, got attracts masses together. Okay. Although this one, universal gravitation, if you get deeper into physics, say like Einstein general relativity, you can actually make the case that this is maybe not a force, or at least it's separate from the other 3. Maybe gravity is more of an artifact of fabric of space-time and space-time bending than a proper force like these other 3 are. Anyway, it's a little detailed, but let's just stick to high school physics one. We'll call that a force, right? And then electromagnetism covers almost everything else that you guys see in this class. So obviously electricity and magnetism, because that's in the name, right? But also chemistry. We talked about that in the last few days, right? Isn't all of chemistry just driven by the location of electrons and valence electrons and atoms, right? Why is the periodic table organized the way it is, right? Why do certain chemical reactions have, right? Why is glass transparent, right? It's all chemistry questions, which relates back to electromagnetism again, right? Contact forces, right? If you push on something, pull on something, string tension. How about a friction force, right? If I drag this across, there's some friction force there, right? That's all under the umbrella of electromagnetism. Okay, so these two are most of this class. Now, since we're getting into quantum, right, here, let's consider what's going on inside the atom. Right, so now we got these other forces. We got a couple of nuclear forces called strong nuclear force and a weak nuclear force. Okay, so like why would all the protons and neutrons hang out together inside the nucleus? From an electromagnetic point of view, that makes no sense. They should all be wanting to repel away from each other. So what's going to count for that is we're going to just call this the strong nuclear force. Now, each one of these forces has a different magnitude and acts over a different range. So gravity is considered to be the weakest of these, right, by far. Electromagnetism is like billions of times stronger than gravity force, and you can know because if you like drop an object onto some surface, right, gravity's pulling it down, but it's immediately stopped by some surface force holding it up, some normal force. That's electromagnetism, right? Easily holds up. But the strong nuclear force is way, way stronger than electromagnetism inside the nucleus, but it acts over a much shorter range, right? And then there's one more we'll call weak nuclear force, and that's going to govern radioactive particle decay. So here, I'll write it with you guys. So we got four forces here, four fundamental forces. We got gravity, right? So attraction of masses. We got electromagnetism, okay? And just to list a couple examples here. So subcategories, I'll put all of chemistry, right, which is an answer to one of your final exam questions coming up. I'll put contact forces. Right, a couple of examples, but I'll just leave it at that. Okay. We have strong nuclear force. Right. I'll say bind nucleus of atom together. And then weak nuclear force governs radioactive decay. All right, and that is as far as I've been getting today. That is our pause point.